Today we will be presenting our project on implementing the spiking neural network on VHDL. So this is just a brief overview of what we will be presenting today. The first section is contains most of the content we presented for the meet, and it contains an introduction, whereas the second section presents the building of the system and VHDL simulation results. So spiking neural networks are considered to be the third gen neural networks, quite different from the second generation neural networks that we use now. The main difference would be that the spike SNN would include the notion of time when they encode data. So there are different methods where we can encode data, which would be like rate coding or time coding, and then there are several different methods where we could use decoding techniques such as rate coding, rank coding, or time to first spike to decode the final output. And the difference between one of the key differences between the normal neural network and the spiking neural network is that the normal neural network would fire for every input, whereas the spiking neural network wouldn't fire. It would accumulate the charge. I would explain that later, but it will accumulate the charge, and once the threshold is reached, it would emit a spike. This is the methodology we followed. We first implemented the basic models, the leaf model and the synapse model in the network, and then we built the spiking neural network. We will be verifying the network using the XOR Boolean logic function, because in the meet we were supposed to do the MNIST, do the verification for the MNIST network, but the input is input contains 784 neurons, and the hidden layer contains around 46 neurons. So for a fully connected layer, actually finding the weights would have been so there was a practical issue, so we thought of going with this. So our network configuration for this XOR Boolean logic function would contain two input neurons for each input, and 4 hidden layer neurons for each state for the Boolean logic combination, and the output layer contains only 2 for the possible logic values of the output. These are the other configurations, for example, the neuron model, encoding and decoding. We also implemented it in MATLAB comparison. This is the spiking neural network components. These are the inputs, and as you can see, the hidden layer contains 4 states, and we for each of the weights for these synapses, we actually manually change the weights and test. If I just briefly discuss about the biological background of the leaf neuron model, it takes current as the input and emits spikes. So based on the current that it gets, it accumulates charge, and then once the membrane potential for that particular neuron reaches a certain threshold, it will discharge and by emitting a spike, and then it will fall back to resting potential. And another key point is that until a refractory period, it will not start accumulating any charge. As you can see in the graph the external input current is constant, and the membrane potential, which is the second graph, keeps increasing. But unless the membrane potential reaches a certain threshold, it will not emit a spike. This is the biological background for the synapse model. The synapse model takes a set of spikes and then emits the current. So as you can see in that particular graph, there are a set of spikes, and for each of the spikes you can see there's a rise in current, but it exponentially decays until it meets the next spike. Finally, putting it all together, we build this leaf neuron and 2 synapses. One synapse will contain a set of spikes, a dense set of spikes, whereas the other would contain 2 spikes. Then those are the 2 graphs displayed those are the first 2 graphs, and the presynaptic current from the first input spike train is displayed in the third graph, and the fourth graph displays the current for the second spike train. Finally, the membrane potential of the leaf neuron keeps increasing until a certain threshold, and it will emit a spike once the threshold is reached. So this part was implemented in MATLAB. So Manithu will explain it further.
Thank you, Sabda. So basically, this is the model that we are trying to solve in this life neuron component. Where for the as the inputs for our life neuron component, we have input currents that are coming from synaptic connections, and then we store a weight vector that for each of the life neuron in an array within the life component, and then we do all of these mathematical operations in order to get the final outcome, which is the post neuron spike train from the neuron model. And then this is the operational flow diagram for the synapse model, and basically this is the equation that we are trying to solve in this model. And we have, same as we have discussed in the interim presentation, the input for this component is a spike train that is coming from either the receptor neurons or any of the neurons in the hidden layer. And then we do all of these mathematical operations to ultimately do integration and then get the postsynaptic current. The only change that we have done here is that we keep an array. We keep all the firing times of the spikes in an array. At the beginning of the system, we initialize all of the array components. This is an array of 64 elements, and all of these elements are initialized to infinity, because at the beginning, where the t equals 0, there are no spikes at the system. So it should return zero synaptic current. So basically, in our system, we first decided that the system will run only for 15 milliseconds, and then at discrete time intervals of 0.01 millisecond, and then we provide the spike train using a spike pulse generator. And then apart from that, we have life neuron model, synapse model, exponential value generator, and then test bench for the neural network implementation, and MATLAB implementation for verification as the other main components of our system. This screenshot is taken from the spike pulse generator, where you can see there are two spike trains that the generator is generating. First one is emitting spikes at a time with the time period of 0.4 milliseconds, and whereas the other one emits spikes at the time period of 0.9 milliseconds. So this is the way that we calculate the exponential value, because we cannot just simply calculate the exponential value in VHDL. First, since these are the two equations that we have to calculate the exponential value. So if we look into these parts that is inside the exponential part in both of the equations, we can just resemble that part into this basic format. So what we did was, since our system is only run for 10 milliseconds and then 15 milliseconds, and then this time constant, that is the either synaptic time constant or the membrane time constant. So in general, that value lies between 10 milliseconds and 15 milliseconds in biological background. So what we thought was, if we can fix those two values, then we can find the range that where we are required to find the exponential function. So what we did is, we found the range that lies between y equal -3 and y equals 0. So we did a polynomial approximation for the exponential curve between these two values, and with the cubic approximation, we could get almost 100% fit. So we used this approximation to generate the exponential value within the VHDL component. So once we did the LIF implementation, we did this experiment. We used these model parameters for the LIF initialization. Membrane resistance as 10 milliohms, and then membrane potential threshold 50 millivolts, and then 5 millivolts as the resting potential, and then tau m, which is membrane time constant, 10 milliseconds, and then refractory period as 1 millisecond. And then for these, just for the sake of the simplicity, we initialize all four weights. Now this is the model that we did the experiment for the LIF model. for all of the waves we set to 1, and then for all of the synaptic current we just set the 2.5 milliamperes. Now here, instead of giving a pulse train, what we are, just for this experiment we gave constant currents, and then you can see there are two spikes that from the resulting spike train. One is around 6 milliseconds and other one is somewhere around 12 milliseconds. For a clearer picture, we did a comparison with our MATLAB implementation. Now we generated these graphs using the exactly the same model parameters and the same approximation. Now you can see for the MATLAB LIF implementation, we provide a 10 milliampere input current, which is same as the summation of all four of these input currents from 4 synapses. And then you can see how the membrane potential changes with the time. Once it reaches somewhere around 6 milliseconds, it emits a pulse. It emits a pulse, and then it waits there for about 1 millisecond, just as the refractory period, and then the membrane potential starts climbing again until it emits another spike. So in this way we can verify both of the implementations works the same way.
What's the hardware implementation of this part?
VHDL.
For example, you are using what gate? Logic gate.
We use floating point operations.
Multiply?
Yeah.
We used several like multiply, adding like several
Okay,
components.
I see. But you show the voltage and the current in this figure, right? No, the next one. The y-axis here is voltage, and the y-axis of the first figure is.
No. These are actually for this one resembles only with this one.
Okay.
So this is just as the internal simulation. We cannot see the internal simulation in the VHDL, so we did that in the MATLAB.
Okay.
So this is how we verified the Synapse implementation with our MATLAB implementation. For the Synapse experiment, we provided input pulse train that runs at 1 megahertz. So effectively, we provide a spike at every millisecond, and then as the synaptic time constant, we use 50 milliseconds. So in this red line, you can see how the spikes are provided into the system, and then so this green bar is supposed to contain all of the contains the vector values for the output current. So what we did is we converted them into decimals at every 0.5 times 0.5 millisecond time steps, and then we generated this graph, and then we did this exactly the same thing in MATLAB, and then we provide the spikes at every 1 millisecond time step, and this is the resulting graph. So you can see graphs are exactly the same, and all the at 10th millisecond it generates a current somewhere around 6.5, which is the same in both of the graphs.
So now I'll be discussing a little bit about the XOR SNN simulation in VHDL. As you can see, that's the final network we are planning to generate, and these are the values that we have given to generate the initial spike pulses. Basically, we need one rate to encode the value 0 and one rate to encode the value 1. The only requirement is that they should be clearly distinguishable, and visually it should be represented very clearly. And this is just an example of building the spiking neural network. We will be having 4 hidden neurons and 2 output neurons. So as you can see, for these hidden neurons, you can see that the spike pulse trains are the input, and the 4 outputs from these hidden neurons, which will be the inputs for the output neurons. And finally, we would be the final output would be given from either output 5 or output 6. These are the initial results for the XOR SNN. Firstly, we used values of rates of 0.5 milliseconds and 3.5 milliseconds. But the problem here was that the SNN was giving outputs that were like all one. So the reason is that the gap between the spike pulses generated for the two inputs is very large. So one would be having a time period of 0.5 milliseconds, but for the other spike train, the pulses would be generated each 3.5 milliseconds, and the gap is too large. So we reduced the gap between those two to 0.4 milliseconds and 0.9 milliseconds, and this gave much better results, except for, of course, the second input, where the first input would be 0 and the second input would be 1. So like we manually also tuned the network weight parameters, but still we were like not able to get good complete outputs, like correct outputs for all 4 scenarios. But that's why we concluded that we need to implement the learning part, which is synaptic time dependent plasticity. It's a type of weight learning mechanism in spiking neural networks in MATLAB, and then of course use it rather than manually updating this. These are the XOR simulation results for input 0, 0. As you can see, this represents output 1, output 0, and this represents output 1. For the first one, we get, you are able to see this first spike emitted here. The first spike is emitted from output 0, so it gives the correct output. But for the second combination, the first spike is emitted here, but it gives the incorrect result. And for the third one, we get the correct output. The first spike is emitted from the network for output 1, and finally for the last combination, we get the output in output 0. So that concludes our presentation.
So as about the learning part, we tried actually to do that in MATLAB and then learn to do the learning, but it is a process that takes time than we have anticipated, because learning SNN is still a research area.
Any question? Yeah, I like your effort in looking for an alternative network topology, like the spiking. Thank you very much.